Newton's first law tells us that motion cannot change without a net force. And his second law is focusing on what happens when you have unbalanced forces. And there's three main ideas that's going to surround Newton's second law. Unbalanced forces cause acceleration. Larger forces cause larger accelerations. And mass reduces acceleration. So all of these are going to lead to a formula that explains the relationship between force, mass, and acceleration. And it's F equals ma. Force is equal to mass times acceleration. And just kind of a couple pieces to go along with this. Here's what F, M, and A stand for. And here's the units that we use. Since mass is measured in kilograms, and we know acceleration is measured in meters per second squared, and we can say force is kilograms times meters per second squared. But an easier way of saying it is 1 unit of force is a Newton, which is just a capital N. All right, so let's take a look at the first main idea that we were just talking about. Unbalanced forces cause acceleration. And I want to take a look at an example here. All right, so here's my Ford F-150, my Ford. If I sit over here and I apply no force to it, then it will not accelerate. Right? F equals ma, 0F, then 0A. This is Newton's first law. And we're at equilibrium right here. It's balanced. Now what's going to happen when I apply a force? Now we're going to have an unbalanced force. So let's take a look. So when I apply the force here, it's going to cause that truck to accelerate. So that first one makes sense. Let's take a look at the second one. It was that larger forces cause larger accelerations. Now, this makes sense in real life in a very easy way, and I'll show you what I mean by that in an example in a second. But we can also make sense of this using the formula from before, the F equals ma. And what I was saying, if we come back to this, large forces cause large accelerations. So if I increase my force that I apply to something, it'll cause it to increase its acceleration. In other words, I push it harder, it moves faster. It goes the other way too. If I decrease my force, it'll decrease my acceleration. They move up and down together. We refer to this as being proportional. That force is proportional to acceleration. They increase together or they decrease together. So here's an example to demonstrate that second idea. So in my example, if a small force is trying to move me, I don't accelerate as much. But if a large force tries to move me, I accelerate a lot more. Our third idea was that mass reduces acceleration, assuming that force stays the same. So take our formula again. If the force stays the same and you increase the mass of an object that you're pushing, it will accelerate less. But if you decrease the mass, make it lighter, you'll be able to accelerate it more. We call this inversely proportional. One goes up, the other goes down. Let's take a look at an example of this. So in this example, I bring my Ford F-150 back, small mass, I apply a force, it accelerates a lot. But if I bring in something that has more mass, my Ford F-15000, and I apply my same amount of force, the acceleration is very low. It doesn't accelerate much at all. Alright, so let's take a look at Newton's second law, and we'll have Isaac Newton himself tell you first. Here it is. The acceleration of an object is proportional to the force. It's in the same direction as the force, and it's inversely proportional to the mass of the object. Our mouths didn't match up very well, did they? That was a mouthful. Let me lay that out on a slide here so you can write it down. You might need to pause it for a moment. But here it is. Everything we just talked about wrapped up into one kind of difficult sentence. Alright, I want to try out a couple of examples now, and we're going to use the F equals ma formula again. But I want you to remember, just like we did with the velocity wheel, you can do the same thing with a force wheel, and it looked like this, where F on top is equal to mass times acceleration. And if you want to solve for acceleration, you cover up the A, and it's force over mass. Or if you're solving for mass, it's force over acceleration. So let's take a look at this first problem. It's on your sheet. An object with a mass of 100 kilograms accelerating at 3 meters per second squared. What's the object's force? So let's work this one out together. Alright, so we know that force is what we're trying to figure out. Our mass was 100 kilograms, and our acceleration was 3 meters per second squared. So it's going to be pretty straightforward. If F equals ma, then we are looking at F being equal to 100 kilograms times 3 meters per second squared. 100 times 3 is 300. Our units could either be kilograms times meters per second squared, or the easier version of that is just to say 300 newtons of force. Alright, here's another one to try out. You apply a force of 25 newtons, so we have the force this time on a 100 kilogram box. What's the box's acceleration? Let's try this one out together as well. So we know the force is 25 newtons. We know the mass is 100 kilograms. What's the acceleration? We can use that force wheel. Force equals mass over acceleration. We're solving for acceleration, so our formula is F over m. A equals F over m. Okay? Just plug in our numbers. 25 newtons over 100 kilograms, and we get an answer. Let's see if we can make a little room here. That's 1/4 or 0.25, and our units are going to be meters per second squared. You know that from acceleration. But let me show you how we get that as well. Remember how I said a newton is also could be known as a kilogram times meters per second squared? Well, your kilograms will cancel, leaving you with a unit of meters per second squared. The last thing I want to look at is projectile motion, and a couple of really simple definitions. A projectile, all right, is an object that is going through the air. All right, going through the air, and gravity is the main force acting upon it. Right. And in many cases, maybe the only force. The trajectory, let me write this down. These are words you've probably heard before. Nothing too new here. Trajectory is the path of a projectile. All right? And projectiles tend to take a path that is called a parabolic path, a parabola. And that's just a nice smooth curve, smoother than what I made here, a nice smooth curve like that. Alright, so the thing I really want to start talking about here is how projectiles tend to move. Now, if we drop a ball straight down and we let gravity accelerate it, we know it'll accelerate at 9.8 meters per second squared. And here we rounded it just to 10 meters per second for velocity. So in other words, every 1 second, after 1 second of falling, it's going 10 meters per second. Every second, it increases by another 10 meters per second. 20 after 2 seconds, 30 after 3, 40 after 4. Right? Now, we also know that if you were to roll this ball across a table with a constant velocity, say you just kept the velocity at 10 meters per second, this ball was able to set a cruise control, that it would go in this direction. Now, the difference here between these two directions is sort of what gives us our projectile motion. If you have an object moving straight out versus an object moving straight down. Now, an idea I want to get across, and this is kind of a hard idea to understand and to accept, but it's one of those things that doesn't seem like it's true, but it is in fact true, that this motion right here, going outward, is completely 100% unrelated to this motion right here. Unrelated. Now, what does that mean? Here's where it gets a little difficult to understand. It simply means that if I were to roll a ball off this table and it took, as I'll show you in a second, it'll take that parabolic curve because it has two different directions acting upon it. It'll hit the ground at the exact same moment as a ball if I just dropped it straight down, because this motion right here is unrelated to this motion. Right? Gravity acts on the ball the same way. It doesn't matter. I could shoot the ball out at speeds, like 1,000 yards a second kind of speed. It won't hit in the same area. It'll be very far away, but it'll still hit the ground at the same time as a ball that I just dropped straight down. So here, and I'll come back to that whole idea in a second. Here's that parabolic motion. You have the two different directions, two vectors acting on this, one in the what we call one in the x direction and one in the y direction. Think of this as a x and y graph here. And it causes, since they're both unrelated and they both act on it sort of equally, it causes that parabolic motion, that curve that we're looking at. Right? So let me come back to another example, and I want to direct you towards a video, a Mythbusters video. And the thing that I wanted to talk about was that this great example. If you shoot a gun straight, right? It has to be straight. You can't shoot it up in the air, but you're shooting a straight bullet, sort of like this ball up here on the x-axis. And at the same time, you drop a bullet. As soon as you pull the trigger, a bullet just drops, and the only thing acting on it is gravity pushing it or pulling it down. This bullet right here, as it gets shot out, very far away, but starts to curve down, will hit the ground at the same time as this bullet that's just dropped. That's where this becomes hard to believe, right? This is what I said earlier about these two motions being unrelated. That didn't seem like too much to have to believe, but to believe that a bullet being shot straight out will hit the ground at the same time as a bullet just being dropped, that's a tough one. But in fact, it is true. And what Newton was saying in the second law and throughout is that these two different directions are acting unrelated to each other. So if you click on the link below here, it'll send you off to watch a video on the Mythbusters where they prove, in fact, that what I was just saying is true. All right, the last thing I really want to talk about dealing with projectile motion, and to end this video clip, is dealing with circular motion, very, very similar to projectile motion. And I guess the one point I want to get across here that's pretty important is there's two forces acting on this ball, right? There's the force connecting it to the guy here, and there's the force of this ball wanting to travel in a straight line. All objects want to travel in a straight line. And because of these two forces acting on it, the ball kind of picks the middle and goes in a circular motion. If you were to let go of it right here, and there's no more of this force pulling it in, it would go straight in that direction. If you were to let go of it right here, right, as the ball comes around, it would go straight off in this direction. If you were to let go of it here, and he's already come around this bend, it'd go straight off in this direction, and so on. Because there's always the inside, the force pulling it towards him because of the chain that's connected to him, and the force of it wanting to go in a straight line.